Welcome to Chemistry 315. My name is Dr. Gor Sarkisian, and this is a course in inorganic chemistry. Before we begin, I would like to go over some of the details of the course and what to expect and how we're going to conduct the course. Basically, this is going to be predominantly an online webinar-based course. We will meet on campus periodically to go over some of the details, do reviews. We will meet for midterm exams and for the final. Now, the presentations will be posted once a week. They will include questions that you are responsible to answer and send to me. The questions will be sent to me within 2 days after the scheduled class. The first one is a bit of an exception, I suppose. But these questions will count for your participation and homework assignment. If the assignment is turned in late, that will constitute absence from the class. You will lose participation points and you will be marked absent from the class. If they are turned in a timely fashion, you will be marked as present and you will receive your participation and homework points. If you turn in your assignment late, and let's define late as 2 days after the presentation is posted. If the assignment is late beyond that, then you will lose participation point. You will be marked absent, but you will retain the homework point. So having said this, I am going to be available upon demand. Let's keep an open communication through emails and other media of interest. And now let's begin with the course. So when talking about the beginning of chemistry or life as we know it, we have to begin at the very, very beginning, which is the Big Bang. Big Bang is the theory that our universe was birthed into existence through a monumental explosion of singularity that within microseconds, nanoseconds, femtoseconds created our universe as we know it. So this event occurred about 14 billion years ago, and several interesting steps are to be noted. So immediately after the explosion, everything was in immense heat, in excess of 10 billion Kelvin. This is way too much kinetic energy for fundamental particles to coalesce together. So besides fundamental particles, there was nothing else. At least in a form that we know of today. Then, following that, the universe expanded and cooled, and this happened fractions of a second later. Obviously, with cooling, the particles started moving slowly, and they began to adhere together under many different conditions. But one noteworthy one includes the short range and yet powerful forces that act between nucleons. Nucleons are basically the constituents of the nucleus, protons and neutrons. So that with that, we have created the first nuclei. Then, following that, still some time later, which is again in a range of microseconds, we observed further cooling and other forces, such as electromagnetic forces, became prevalent. Electromagnetic forces are weaker, but they act at longer range. These are the attractive forces between charged particles. Shall we say particles such as electrons and protons? So these forces allowed electrons to bind to nuclei to form atoms, which was the first step towards the complex chemistry that we will be studying today, this semester. Only about 2 hours into existence, most of the matter in the universe was hydrogen and helium, two of the most basic elements. But at this stage, the temperatures had fallen so much that the prevalence of nuclear reactions allowed for a formation of a plethora of elements which are heavier than helium and hydrogen. And basically this was the step in which the chemistry as we know it became possible. When speaking about nuclear reactions when it comes to chemistry, we have to talk also about nuclear binding energy. Now, nuclear binding energy is basically that defines how stable the nucleus is. And obviously, the higher the energy, the more stable the nucleus is. This energy, if you remember from your previous courses, I hope you do, is measured in electron volts. And as a refresher, an electron volt is the amount of energy gained or lost by the charge of a single electron that moves through an electric potential difference of 1 volt. Now, obviously, the larger this force is, the more stable the element is. Now, the funny or interesting peculiarity there is that elements with even Z number, atomic number, and I hope you remember the Z number from your previous courses also, the elements with even Z numbers tend to be more stable. They have higher binding energy per nucleon than elements with odd nuclear numbers, atomic numbers. So, question number 1. Why is this so? Now, we did not talk about this in thus far. However, this is a question that you should be able to answer based on the introductory chemistry course. Now, we talked about the differences between elements with odd and even Z numbers, and on these charts, you can clearly see elements with odd Z numbers, atomic numbers, have significantly lower nuclear binding energy than those that have even Z numbers. And remember, these are in log scale, okay? So these are significant differences here. So we started talking about nuclear energies, the binding energy. Let's talk about now about fusion, nuclear fusion, and nuclear fission. So when two nuclei come together, which are lower than 56 in Z number, they can merge together and form an element of a larger nuclear number or nuclear binding energy. So let's consider two neon nuclei coming together. Neon has a Z number of 20, which will produce a calcium-40. Okay. Now, the energy per nucleus, energy binding of neon is 8.0 mega electron volts. Okay. So what happens here? We have two neons. Here we took two neons here. We multiply that by the Z number and then multiply that by 8.0 mega electron volts. And that yields 320 mega electron volts. Okay. Now let's look at what calcium-40 is. Calcium-40 has E binding of about 8.6 mega electron volts. And the math here is easy. It's 40 times 8.6 mega electron volts, which yields total of 344 mega electron volts. And this is a fusion reaction that releases 24 mega electron volts. Now, nuclear fission happens with elements that have an A number more than 56, and it has to do with internal forces within the nuclei. So, for this scenario, let's consider an element, uranium, which has E binding of or rather E binding over A of 7.6 mega electron volts. Okay, and uranium is quite a heavy metal, and that fission can yield a xenon and strontium. Okay, and plus proton. So, as I noted, the nuclear binding energy here for uranium is 7.6. For xenon, it's 8.4, and for strontium, it's 8.7. Okay, so let's add it all together. We have 140 times 8.4. That's our xenon. We add 93 times 8.7, our strontium, and then we subtract, right, the uranium 236 times 7.6, and that yields a total of 191.5 mega electron volts released during the fusion of uranium-294. So here is question number 2. We have a list of particles: electron, proton, neutron, photon, neutrino, and others. Please describe what each of these are, briefly. One sentence, perhaps associated energies, and where these are originated from. We have several different techniques in our disposal to describe chemistry, and one of them is spectroscopy. Spectroscopy is basically determining the electromagnetic radiation that is emitted from the element, the atom, when it's electrically excited. The model atom for spectroscopy is hydrogen, or hydrogen gas, rather. Why? Because it has very little electron interference as opposed to others. So we use that as a model. Okay. So when we excite a hydrogen gas, so basically we pass a electric charge through a cloud of hydrogen. That emits light. Light is an electromagnetic radiation. It's energy. It emits energy. When this light is passed through a prism or a diffraction grating, that light is decomposed into its individual components. Just like when one uses a prism under a sunlight, we see a rainbow because the electromagnetic radiation from the sun is more or less continuous throughout the visible spectrum. So when we excite a single hydrogen gas, only pure hydrogen gas, we get several lines. One in ultraviolet, a couple in the visible, and in infrared. So here is a typical spectroscopy output of several excited gases. Hydrogen, as you can see on the left, is fairly simple. It has only a few lines, and we will discuss why. Then we have helium, and we have mercury. And as you can see, they're also very different, but these spectra are very unique to a given atom. Now let's explain this phenomenon. From this point on, I will assume that you are familiar with the basic concepts of molecular transitions, of electron interactions that you should have learned from other chemistry and physics classes. Now, please, by all means, if a concept seems foreign to you, stop me, ask to explain some aspect of this a little further, and I will gladly make a class dedicated to filling in the blanks, okay? So I would rather not go all the way through a defined course and deviate a little bit to explain further some of the details than just zip right through without you guys completely being vested or understand what's happening. So anyways, having said that, let's keep going. And one of the big steps forward in this quantum chemistry was done by Johann Rayberg, which basically found that the wavelengths, lambda, can be discrete. And defined or calculated with rather simple relationship in which inverse of wavelength is a product of constant multiplied by 1 over n1 squared minus 1 over n2 squared, in which this constant, Rayberg constant, is an empirically calculated constant, okay? So n1 is a series of 1, 2, 3, and so on. The n2 would be a series of n1 plus 1, N1 plus 2, and so on. Okay. Now, it is important to note that these numbers, the N1s, which can be 1, 2, 3, 4, and so on, at least in the first several lower orders, which are more applicable to our course, to chemistry, are labeled as predefined series like Lehman series, Balmer series, Paschen series, and bracket series. Okay, and these basically define the energies of the photons or electromagnetic radiation that are released. Now, n being 1 and 1 equals to 1 is the primary quantum number. This is the lowest energy level. It is important to remember that, and we'll find out why shortly. We can visually show this on this diagram. So we have our visible spectrum roughly from 800 nanometers to 400 nanometers. And here are the 4 well-defined series. And in this case, these lines would be the lines of emission or absorption of an element, of an atom. Now, if it emits light at a particular wavelength when it's excited, it must also absorb light or radiation or energy at that part corresponding to that wavelength if it's being irradiated by a spectrum of light. Now let's look at what's happening in a bit more detail. Now, you should remember from previous physics courses and the laws of thermodynamics that the energy is conserved, right? And we've been talking about energy transitions here, and N number basically denotes these energy transitions. And N1 is always lower order than N2. Therefore, transition from this energy level to this results in emission of energy. So if we subtract one from another, we get this expression. So HCr, and I hope you remember what H is. H is the Planck's constant, which is 6.626 times 10 to the 34 joules. C is the speed of light, and R is what we have already talked about, is the Rayburn constant. So now the energy that is released is, of course, denoted as hc divided by lambda. And I hope you also remember this from the basic physics course. Again, h is the Planck's constant times speed of light. So this term right here equals to hc divided by lambda. Therefore, we can easily cancel out the hc's, and we get the formula that we have already encountered a few slides prior. So our energy released is directly proportional to this energy transition right here. Now, there are many different ways to denote energy, right? We can either denote it as in terms of wavelength, lambda, or we can denote that as a wave number. Now, wave number has to do with energy more than light, so for practical purposes, we will use wave number. Before we go forward and possibly introduce some more confusion, we need to first define some simple terminologies and relations. So a wave number we talked about. So what is wave number? Wave number is basically the number of waves or wavelengths in a given distance. So wave number of 1 centimeters minus 1 denotes one complete wavelength in a distance of 1 centimeter. That's it. A related measure to wave number is frequency. Now, if you see, this does not have the line on top, and actually the wave number has is in Greek V, whereas frequency is the regular English V, or Roman, I should say. So frequency is simply the number of times per second that the wave travels through a complete cycle. Okay? It's denoted in hertz. So 1 hertz is 1 full cycle per second. So they are very well related to each other with a very simple relationship in which frequency is inversely proportional to wavelength. So even though the wavelength of light we usually denote as nanometers or picometers, the wave number, given that it describes a more internal energy state, is denoted in centimeters minus 1, or reciprocal centimeters. A natural question is, which I'm sure you are asking right now, is why is the energy of electron in an atom limited to this value of hcr over n squared? And why r has a value that it has? Now, again, r is a value that was deduced empirically rather than calculated. Now, to answer this, Niels Bohr in 1913, using the early form of quantum theory, was able to characterize it. So he did show that electrons could exist in only certain circular orbits. He did obtain the correct value of r, but his model was untenable. It conflicted with later versions of quantum theory developed by Schrödinger and Heisenberg, which I hope you at least heard of. So, next several slides, perhaps until the end of this presentation, we will go through this theory and understand it fundamentally, because it is very important to be able to do anything that has to do with chemistry. But first, let's try to solve this simple example problem in which we will try to predict the wavelengths of the first 3 lines in Balmer series. Now, Balmer series, we know from previous slides, and you should know this, that N1 in Balmer series is 2. Therefore, N2 would be 3, 4, 5, 6, 7, and so on. Okay? Now, utilizing the fundamental equation that we've described already, 1 over lambda equals r times 1 divided by now 2 squared minus 1 divided by 3 squared. From here, we can calculate that 1 over lambda equals 1513888 meters to the minus 1. or it's the same thing as lambda equal 661 nanometers. Okay. Now we wanted to find out the second line also, right? So for the second line, we use the second in a series of n2, which is 4. And the same thing, 1 over lambda equals r 1 divided by 2 squared, now minus 1 divided by 4 squared, which in turn equals to lambda equals to 486. And then if we substitute the next one for the third line, sorry about that, it would be 5 squared, which would be the lambda equals 434 nanometers. And so on and so forth. Therefore, we can calculate the emission lines of any of these transitions. And these transitions will be discrete. So before going on to describing some of the principles of quantum mechanics, let's summarize what we gain from spectroscopic information. Basically, the spectroscopic observations of hydrogen atoms suggested that electron can occupy only certain energy levels, and that the emission of discrete frequencies of electromagnetic radiation occurs when the electron makes a transition between these energy levels. So now let's do another assignment, which is fairly simple. Let's try to predict the wave number and wavelength of the second line in a Paschen series. So the wave number of the second line in the, sorry about that, Paschen series. So now let's begin examining some of the principles of quantum mechanics. So in 1924, Louis de Broglie attempted to describe some of these phenomena. So he stated that if an electromagnetic radiation is a particle, a photon, and has a wave-like property at the same time, basically as a wave it can elicit interference and diffraction, and then if this is true, then the same phenomenon might be true for an electron. Now, this dual nature of a particle and wave-like properties is called wave-particle duality. This duality has some problems, well, not the duality itself, but the duality results in some problems, such as it is not possible to measure the linear momentum, which is a vector of mass times velocity, and the exact location of the electron at the same time, or any other particle for that matter, elementary particle. This is explained by Heisenberg's uncertainty principle, which basically states that the product of uncertainty in the momentum and the uncertainty in the position of the elementary particle cannot be less than the quantity of the order of Planck's constant. Now, we have Planck's constant right here, and we have to, of course, we earlier defined that, or let's define, electrons can only revolve in an orbital, right, whose angular momentum is integral multiple of this term right here, okay? So basically, it is the 2 pi is denoting the angular momentum. So this is same as Planck's constant, but with an angular momentum. Now, if you remember, the Planck's constant is 6 times 6 times 10 to the minus 34, something like that. And then imagine dividing that by 2 pi. And then further dividing it by half, it becomes an extremely small number. So any attempt to measure precisely the velocity of an elementary particle will knock it out of its physical location in unpredictable way. Therefore, the simultaneous measurement of position and its velocity loses all validity. So obviously this duality was a fundamental problem. But then Schrödinger formulated a very elegant equation that did take in account the wave-particle duality and accounted for the motion of electrons in the atom. He introduced that concept of a wave function, a psi, which is basically a mathematical function of the position in coordinates x, y, and z, which describe the behavior of an electron. Now here we have Schrödinger's equation. As you can see, this is only for a single dimension, only for x dimension, but it's fairly straightforward to obviously convert into a three-dimensional x, y, and z. Now in this formula, we have the kinetic energy contribution, we have the potential energy contribution, and of course the sum of both results in a total energy. Now this is an elegant solution because from this equation it becomes obvious that there are some boundary conditions that we do not need to worry about right at the moment. We will talk about this in the future. There are some boundary conditions which restrict what values the E, the total energy, can have. So therefore, the phenomenon that a photon can have a discrete, or rather, let's say the energy transition could be of a discrete or have discrete value, simply naturally flows from the Schrödinger's equation. As such, the wave function contains all the information possible about the electron, where it is, how fast it's traveling. But a problem is the Heisenberg's uncertainty principle. This seems to be violating the Heisenberg's uncertainty principle, which is not possible, which states, obviously, that it is impossible to know all this information simultaneously. So, in combination, this actually works in terms of probability. Therefore, the wave function is a means to find the probability of an electron being at a particular location. More specifically, the probability of an electron being in some particular place in space and time is proportional to the square of the wave function. And it's fairly straightforward, fairly simple. High probability of finding an electron where wave function, the psi square is large, and the electron will not be found where psi square is 0. So the quantity of psi squared. Psi squared is basically the probability density of the electron, and it is product of psi squared times delta tau. And delta tau is a tiny point in space defined as obviously dx times dy times dz in 3 dimension. And that is it's proportional to the probability of finding the electron in that volume. Okay? So if we normalize this delta psi times delta, the psi squared times delta tau, if we normalize the whole wave function to be this entire thing to equal to 1, basically we state that the electron is definitely somewhere between these two spots in a wave function. That wave function, therefore, is for the electron in the atom is therefore called the atomic orbital. Okay? Even though we don't know where exactly the electron is within this orbital, we can only find the probability, and the probability of that electron being here is much greater than anywhere else. Probability of that electron being here is close to nothing. And given that it's psi squared, obviously the probability is always positive. It's a probability. And to basically keep track of the signs, it's a wave function nevertheless, right? We basically have negative and positive phases, which are slightly different denoted. In a wave function here, it's easy to see up and down. In a probability density, we have dark shading and light shading. So the wave function is not unlike other waves, and keeping track of the positive and negative phases becomes very important, because all waves have positive and negative amplitude, as you know from the wave theory. Sign is important because when two waves, or in our case of wave functions, propagate in the same area and in such a way that the positive amplitudes coincide, they have an additive effect. They undergo a resulting constructive interference. Constructive interference. So basically, when we're talking about two atoms that are close together, there may be a significant increase in probability of finding the electron in that particular region. Now remember, the wave function and the probability of the wave function would be our phi or psi, the probability density would be the psi squared. So it would be all positive, obviously. So, but at the same time, the opposite might also be true, in which the phases might be off sync, in which the positive amplitude and negative amplitude of two wave functions find themselves in what's called destructive interference, and they cancel each other out, which overall reduces the probability of electron being found in that region. So the overall take-home message is that electrons also can behave as particles or waves. The Schrodinger's equation gives us the wave function, which describes the location and particle of electrons in the atom. The probability of finding an electron in a particular location is proportional to the square of the wave function. The wave function generally has regions of positive and negative amplitude, which upon two atoms interacting may yield a constructive or destructive interference. And in the case of constructive, it increases the probability of the electron being in that particular area. And in the case of destructive interference, the probability of the electron being found there is reduced. Talking about the wave function casually leads us to atomic orbitals. Each of the wave functions obtained by solving the Schrodinger's equation for a hydrogen atom, as we've been talking thus far as a model atom, is uniquely labeled by a set of three integers called quantum numbers. So what are quantum numbers? The three quantum numbers include n, which is called the principal quantum number. The second one is L. Second one is L. It characterizes the orbital angular momentum. And ML, which is the magnetic quantum number. So each of these quantum numbers are very specific physical properties of the electron. N, for example, specifies energy. L is a magnitude that quantifies the orbital angular momentum. And ML is it characterizes the orientation of that angular momentum. In addition, the value of n is indicative to the size of the orbital, in which large n means high energy orbital, more diffused. Low n conversely means compact, tightly bound, low energy orbital. The value of L also indicates the angular shape of the orbital, with the number of lobes increasing with L increasing. And finally, the value of ML also indicates the orientation of these lobes. We will talk about this in great detail soon. Now let's further examine the energy specified by a principal quantum number n for our model atom hydrogen, with an atomic Z number as indicated here. Now, imagine if our n approaches infinity. That basically denotes that energy is zero. And that in turn means that the nucleus and the electron are separated. And therefore, the energy corresponds to the unbound state of the electron. And if an electron is unbound, it can have basically any velocity and it can have any energy. But if we talk about discrete small n numbers, obviously the energy is negative and it's quantified. And because the energy is technically reversely proportional to n squared, the energy levels, as you can see here, they converge as n becomes larger. Now the value of L specifies the magnitude of the orbital angular momentum. As we've stated already, we can think of L as indicative of the momentum with which the electron circulates around the nucleus over the lobes of the orbital. The third quantum number, which we'll discuss a bit more in detail later, the ML, basically specifies the orientation of this movement. For circular orbitals, it could be clockwise or counterclockwise. Now let's go a step further and talk about the atomic shells. So all orbitals with a same value of n will have the same energy, and therefore these are said to be degenerate. And then energy level is degenerate if it corresponds to two or more different measurable states of a quantum system. And in our case, an atom is a very well-defined quantum system. So the principal quantum number defines a series of shells of the atom, or a set of orbitals with the same value of n, and hence with the same energy and approximately the same radial distance. By radial distance, I mean the distance between the nucleus and the electron. So the orbitals belonging to each shell are classified into subshells. They're distinguished or defined by the quantum value of L. For a given n, we can have L being 0, 1, and so on until n minus 1. So the total of n different L values. So for example, if n is 2, then L could be 0 or 1. If n is 3, then L would be 0, 1, or 2. It is also a common practice to write it in a slightly different way. So let's say the value of L It could be 1, 2, 0, 1, 2, 3, 4. And I hope you remember now that subshells can be designated as S, P, D, F, and G. So, for example, shall we say if we have, let's say sodium, right? We have 2 electrons, first shell, we have 1, 2, 3, 4, 5, 6, 7, 8. In a second shell, and we have 1, 1 in the outer shell for a total of 11 electrons. Here is a nice image to show the relationship between shells, subshells, and orbitals. As you can see, the subshells are individual components of the shell, and the orbitals, in turn, are the individual components of the subshells. So the subshell with the quantum number L consists of 2L plus 1 individual orbitals. These individual orbitals are distinguished by the magnetic quantum number ML, which is in turn equals to 2L plus 1, and it's an integer value between plus L to minus L. This quantum number specifies the component of orbital angular momentum around an arbitrary axis. So for example, the D subshell of an atom with L equal 2 consists of 5 individual atomic orbitals that are distinguished by value of ML, which equals to plus 2, plus 1, 0, minus 1, and minus 2. So 5 individual atomic orbitals. F subshell, which corresponds to L equal 3, consists of 7 individual atomic orbitals with values of plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. Now, having everything compiled into a single cohesive structure, what are the practical conclusions when it comes to chemistry? Well, they're simple. There is only one orbital in an S subshell. When L is equals to 0, it's the only one ML equals 0. This orbital is called the S orbital. There are 3 orbitals in a P subshell. This is when L equals 2, and ML subsequently equals to plus 1, 0, or minus 1. These orbitals are called the P orbitals. And there are 5 orbitals in a D subshell where L is 2. And so on and so forth. So as you can see here, we have, for example, this here denotes a single orbital. Individual orbitals. Now, this would be a single subshell, and the whole thing that encompasses the n number is the shell of an electron, of an atom. So now to test your understanding, let's solve the following question. Which set of orbitals is defined by n equals 4 and L equals 1? How many orbitals are there in this set? So we need to first remember the principal quantum number n identifies the shell, and the orbital quantum number L identifies the subshell. So subshell with L equals 1 consists of p orbital, right? L equals 1, that's p orbital. The allowed values for L being 1, which are ML, that would be +1, 0, and -1. Okay. Therefore, what we have is we have 4 p orbitals. So here's a homework question. Which set of orbitals is defined by a quantum number n equals 3 and L equals 2? How many orbitals are there in this set? So here's a homework question. Which set of orbitals is defined by a quantum number n equals 3 and L equals 2? How many orbitals are there in this set? With this, we will conclude our lecture for today. Please submit your homework questions in a timely manner. Shall we say you receive this on Monday? I would expect the assignments to be turned in email to me by Wednesday. So please indicate the course number, which in our case it's Chemistry 315, followed by your name, followed by the assignment. Okay, please follow this naming structure carefully, because I have quite a few students and all of them are turning in their homeworks via email, and I have a sorting algorithm that puts everything in its place, and if it's not in this format, I may not find it, which would not be a good thing for us. Anyways, so thank you very much. Please email me any questions you may have, and I look forward to your questions. Please note that usually there would be 10 questions, but in this presentation I have maybe 3 or 4. So the list of questions is actually attached in the assignments section of Populi.